Hey everybody, this is a video for my Intro Calc students, and this is actually going to be a little more notes and thoughts about, let me see if I can focus that a bit better. There we go. This is a little more support for chapter 2.1 where we introduce the concept of derivatives. And remember that a derivative is of course just, well, it's kind of what we did in chapter 1. It's the slope of a curve, but instead of being a slope of a curve at a point, it's really going to be the equation for the slope everywhere around the curve. That's what we're going to call basically the derivative. And we should talk for a few minutes here about, we'll call this derivative notation, because there's actually several different ways to denote that you're working with a derivative. The one I introduced you to yesterday is that, given a function f of x, its derivative is f primed of x. And again, that's not a power of 1. That's like a little apostrophe. It's a prime. And of course, for example, we saw yesterday that if you had the function f of x equals x squared, then f primed of x, its derivative, is actually 2x. And please notice that that prime can also be used even if you don't want to use function notation. If you just said y equals x squared, then the derivative of that function is y primed. So the primed is kind of the easiest and most shortcut way to show the people looking at your work that, oh, you're doing derivatives. But it's certainly not the only way. In fact, maybe the most common way is something called Leibniz Notation, which looks like this. Basically, f of x primed could be also written as y primed. It could also be written as something called the derivative of y with respect to x, or dy by dx. So this one you'll see a lot for the rest of this course. This is in some ways kind of the favorite notation for a lot of people. And even this can be written other ways. Some textbooks show it like this: the derivative with respect to x of the function f of x, which is a little more formal, but it really says the same thing as all these other things. And sometimes you'll even see capital letters used. The derivative, capital D, of the function f of x is equal to the derivative of x, the derivative with respect to x for the function of y. Yeah, all of these 1, 2, 3, 4, 5, 6 things all basically say the same thing. And if you're wondering why do you have so many different notations for a concept that's actually, once you kind of get your head around it, fairly easy. I just want an equation that represents the slope everywhere around a curved function. Well, it's because calculus was arrived at or developed in multiple places around the world over time, and all of these different notations got popular in different places, and a lot of them never really went away, even when most of the world started doing calculus basically the same. Maybe closer to the weekend I'll find there's some really good videos on YouTube, one that's in my head specifically, that actually talks about the history of the development of calculus, and the two people who we credit with the invention of calculus, Sir Isaac Newton and Gottfried Leibniz. And I think it's actually pronounced Leibniz now that I think about it. But anyway, Newton and Leibniz, of course, had an absolute clash as to who truly invented calculus. And Sir Isaac Newton, I guess you'd have to say, won because, well, he cheated. He was the president of the Royal Society that at the time decided that, oh, we'll credit Sir Isaac Newton with the discovery. It's kind of a long and interesting story, but it set back Sir Isaac Newton was British. It set back British calculus probably 100 years because they were stuck with his clunky notations, whereas Leibniz notation like this, or maybe even like that, is actually very easy to use and easy to understand. So basically, all of the above, I meant to write A, above notations say derivative. And What if you were doing a derivative? Well, new definition for you. As an operation, we say that you differentiate a function in order to find its derivative. So when I, in the last video, used the first principles formula of a derivative to turn this into that, you could say I was differentiating it. So that leads us to kind of our next, well, one more thing on notation. Again, I'll actually write the name down. In Leibniz Notation, finding a derivative, and if I'm writing faster than you, feel free to pause or slow me down. Finding a derivative at a specific point, which we could say as f prime of a, is written like this. The derivative of function y with respect to x of the function when x equals a. So you get this kind of big line that says, I want to find the derivative and then make the derivative specific to point A. Or sometimes you'll see that bracket kind of closed in on the derivative part, a little more like that. And that's the notation invented in the 17th century by Gottfried Leibniz that we still use to this day. And that kind of leads us to, okay, so if differentiating is the act of finding a derivative, we need to talk about when you can and can't do that. When can you find a derivative? In other words, when and when isn't a function differentiable? So that'll be kind of our next little topic here. We'll call this differentiability. There's a 25-cent word. Did I spell it right? Probably. Differentiability. So we would say a function is differentiable. In other words, I can differentiate it, I can find a derivative at f of a if f prime of a exists. In other words, if the slope exists at x equals a. So when would it not exist? Well, funny you should ask that. On a graph, you can see three types of points where a derivative, in other words, slope, doesn't exist and a function would not be differentiable at those points. And here's the three. I'll show you a nice picture of them before I try drawing my own sketch. They look like this. The three types of places where you can't differentiate a function are when the function makes a corner or a discontinuity, remember those from last chapter? Or you get a tangent that is a vertical line. So say, for example, this was a circle at the point here where you'd have a tangent to the circle that's straight up and down, straight vertical. you would say you cannot differentiate. You can't have a slope here. You would almost call this an infinite slope. And of course, infinity is not a number, so that's not a slope. Discontinuity, of course, again, how do you find the slope at this point, or really at that point, the solid one? Because remember what a tangent is, right? A tangent is a line that touches a curve at one place. So if I'm over here, there is going to be a point where that touches the curve exactly at one place. But what about this point up here? Well, I could draw infinite points that exactly intersect with this corner, right? That would be a line that touches it once, and that would be a line that touches it once, and that would be a line that touches it once. I could make infinite lines that would touch this exact point. That's why a corner, also known as a cusp, is not a differentiable point. There's no slope that exists there, right? It's different than a curve. See, a curve does have a slope. There is exactly one line that'll touch the curve at that spot, and it looks to me like it's going to be the slope of 0. We've talked about that already. Further along the curve, again, there is unique instantaneous changes of rate, which we'd call instantaneous slopes, and those together change as a variable, which is why I can make a function for the derivative all the way up to about there, and then the derivative wouldn't exist at that point. So I'll try sketching those. So A is when you have a cusp or a corner. For example, suppose I had, again, so this is my y. Oh, sorry, I'm off the page. This is my x, and I had some sort of function, f of x, that was doing this. It is a function, right? It passes the vertical line test, but as you can see, at that point, not differentiable here, because there is no unique slope at that point. Now, if that's kind of a strange looking creature to you. You've probably never seen an equation that looks like that before. But you know, you have seen something sort of similar. Here's another example. Another example of the same thing. Suppose I graphed y equals the absolute value of x. Remember what that looks like? Y equals the absolute value of x. Let me draw it in a pencil. Starts at 0, and then of course it's a v, right? One arm going that way, one arm going that way, right? Can I differentiate that when x is 0? Nope. Not differentiable. Sorry, I'm off the screen again. Differentiable at f of 0. Because again, what would the slope look like here? Well, does it go this way, or does it go that way, or does it go that way? Well, technically, I could make infinite lines that touch that particular curve at exactly one spot. So, cusps and corners cannot be differentiated. That's just one, right? The other two are B, you can't differentiate at a discontinuity. And again, I'll kind of copy the example they had. The example they had was something like, if you have, this is the y line, and this is the x line, something like a curve going this way that has an open dot here, and then right underneath it, the solid dot, and then it goes, say, that way. So this obviously, say that this was A, not differentiable at x equals A. Or you could also say f primed of A does not exist. Okay? And finally, the third type is, what if you find a place in the graph where you have a vertical slope? And again, the example they gave, I'll try to draw this one to the best of my abilities. As you can see, I'm no artist with this stuff. Something like that, and you have a curve that goes like this, and then it flattens out, and then it goes like that. Well, this flat part here, not differentiable. And that's because, again, you can't say that a slope can be infinite. Infinity is not a number. It's not really a value. Maybe another example, again, I think I mentioned this a minute ago, didn't I? Think of a circle. A circle could have a slope, or a tangent, I should say, all the way around it, but it wouldn't have a derivative at the tangent that I just put as a dotted line there, because that would be, of course, a vertical. So if this is f of, well, actually, this is not a function, so I shouldn't call this f of x, so no derivative exists here. Oh, I guess I should probably put or here. And if you're wondering, what do you mean that's not a function? I mean, I can make an equation for a circle. Did you actually know that there is a nice little equation for a circle? The equation for a circle is, for example, x squared plus y squared equals 1 would be a circle that sits at 0, 0 that has a radius of 1. So this would be a circle that maybe has a x, let's see, it looks like the center moves over 1, 2, so that'd be x minus 2 squared, and it looks like the center moves up about 3, so that'd be y minus 3 squared, and it looks like it has a radius of 2, so that equals 4. There you go. That roughly would be that circle. How come I can't do a derivative for it? Well, first of all, it's not a function, because remember, it fails the vertical line test, and there are places where you could differentiate parts of it, but as soon as you got to where the derivative is straight up and down, vertical, nope, it would not exist. Okay, so there's the graphing part. Of course, most of what we do isn't graphing. Most of what we do is going to be more algebraic. And for algebra, instead of thinking points, you can think intervals. So you could say a function is differentiable over an interval if a derivative exists for every number in that interval. So as long as all your x numbers don't have any points that are cusps or discontinuities or would have a vertical slope, then you've got yourself a section of curve where it's differentiable over the entire section. And a good example of that, again, is the one we just talked about. For example, f primed of 0 does not exist for f of x equals the absolute value of x, right? Because right at that point you have a cusp or a corner. And I'd say, since there is no distinct slope at f of 0. Okay, so there's my example there for differentiability. And that's pretty much where we're going to basically stop for now for 2.1. And I want you to work on the 2.1 questions in the book. Let's see. I'll put up on the blog which numbers I want you to do, but it's going to be quite a few of them. And I'm also going to hand out in class, if today's your day to work at home, don't worry, I'll have a hard copy for you when you get here tomorrow. I'm going to hand out an extra example, and I'll probably make a video where I go through that example, where we want you to use the first principles again to find the derivative, and then I want you to graph both the graph and its derivative, and then some more questions like the one in the assignment where we compare graphs to their derivatives. Now remember, the slope of this thing everywhere is the same, so which of those lines is always the same value? Let's think about that. This thing is going to be some sort of x squared. What kind of a... You know that derivatives are always a 1 degree down from their original function. So if this is an x squared, I'd be looking for something on here that would be an x. And then, hey, we just talked about this guy. I could find a derivative down here, I could find a derivative up here, but I couldn't find a derivative at 0. So which of those would be the derivative of that? Okay, so cool. This is going to be like a little booklet of things like that with graphs that you can work at, and I'll put this page in it too, and I'll make a little video to go through those. And that's about it for now. That takes us to the end of 2.1. Next video we'll do a little bit of grade 11 review again. So work hard on 2.1. Thanks for watching.